All right, so this is plate tectonics. So this is the 16th century global map. You can see that the continents look fairly similar to what they are today, right? Now this is just one of the first maps that was ever made. This isn't because of any changes, but this is what the first map makers came up with. And you can see familiar shapes. I mean, obviously there's some big differences, like the size of Canada versus the rest of the US, the size of South America and the shape of South America. But what do you notice here? Do you still notice that even though everything looks a little squishy, a little wonky, it almost looks like South America and Africa look like they fit together? Absolutely. So let's look at a more modern map. Let's look at a map that looks like today. You see here that South America and Africa do fit really well, as do other parts of the globe. But is the fit absolutely perfect? No, of course not. Why wouldn't it be perfect? Now, this is a little bit difficult to discuss with your neighbor, of course, this is a video, but pause it for a second and think about it. Why would the fit not be perfect? All right, so maybe you're thinking that sea levels have changed through time. They absolutely have. That could affect it. Maybe things have eroded. Sure. Now look at Florida. Do you see Florida on this map? Florida's right here. Of course, we live there. Florida actually doesn't belong here. When these continents were connected, Florida wasn't born yet. Florida is very young. It's the baby of the United States, geologically, of course, not historically. So this leads us to the idea of continental drift. You see that the continents are connected. You know that they look very similar. You probably recognized that as a kid when you were looking at a map. Many do. So Alfred Wegener, a German geophysicist from the 18 and 1900s, also thought there must be a coincidence, or it must be more than a coincidence. So, first off, please don't feel that you need to memorize scientific names here. What I mean by that is I'm not going to test you on Alfred Wegener and what he came up with. I'm much more interested that you understand the concept of continental drift. Okay? But continental drift, he came up with it in 1915, and the idea is that all continents have slowly drifted across Earth's surface. He named the jigsaw continents all fitting together Pangea. Pan means global or worldwide. That's where it gets its name from. So this is what Pangea would have looked like. This is an adorable t-shirt. There you go. All right, so if the continents were connected, we should see other evidence, right? We shouldn't just see a coincidental fit of South America and Africa. We should see something else. So what would you expect to find? Okay, so first, you might expect to find the continuity of ancient mountain belts. So when continents crash together, we can make mountains a lot of the times. When continents pull apart, those mountains don't just go away. They can be split across two separate continents. They can go on one, the other, doesn't really matter. But if we put North America and Africa together again, we see that there was a central Pangean mountain that was found on the eastern coast of North America and the western coast of Africa. You might be thinking that you know that there are mountains on the east coast of the United States, the Appalachian Mountains. Well, are there mountains on the western coast of Africa? There absolutely are. Here are the Anti-Atlas Mountains down here of Morocco, which is northwestern Africa. And here we have the Appalachian Mountains of North Carolina. All right, this is the Blue Ridge, but the Appalachians extend much further out of North Carolina. These mountains were actually formed during the same time, during the collide of North America and Africa in the making of Pangea. So the Appalachians continued through multiple other orogenies, which is just a fancy word for mountain building event. But there you go. All right, so we also see the continuity of major faults. And what that means is, what that means is fault lines, or things like earthquakes. We've got displacements of rock, like the San Andreas Fault. Well, things like the San Andreas Fault actually continue across multiple continents. We find those same things from South America all the way to Africa. Okay? So here are those fault lines highlighted in these red circles. There's one, there's the other. They match up perfectly. We'll worry more about what this line is here by the end of lecture. Now we also see something here. This is a global map, of course, and the gray areas like here, here indicate where we found glacial rocks. Now, what's weird about that? Well, if you've ever been to Africa by the equator, you would know that there are no glaciers. In fact, it's pretty darn warm. If you've ever been to India, you would know that there aren't any glaciers, or Australia, or these parts of South America. These are all areas that are quite warm. Why the heck would we have glacial rock or glacial debris from those times? Well, what if the continents had moved? Let's take a look at what that would have looked like. If we put all of this together, it looks like this. This makes a heck of a lot more sense than this does right here, doesn't it? So this is what a glacial rock looks like. This is a very famous one. This is the Dwight-Tillite from South Africa. So this is one of the original pieces of evidence here. So we can tell it's a glacial rock based on things like this, these giant hunks in mud. That's a really nice indicator that it's glacial rock. We would also see something with fossil distribution. What we see are animals and plants like Glossopteris here, this fern, or Lystrosaurus, this critter here, that clearly cannot swim, being found on multiple continents. Well, that really wouldn't make sense, would it? If it can't swim, how's it getting from place to place? Well, there's not really a whole lot of information unless these continents were connected. There was an alternative idea, and that was land bridges, just like the land bridge that does exist today that connects parts of Russia and North America. So this was exposed thousands of years ago, and humans did come across it at one point in time or multiple times throughout human history. It has since been buried underwater, but scientists before PlateTectonics thought possibly there were like 20 land bridges that connected all the continents together, but there's no geological evidence for that, so we're not going to worry about that idea. So, let's sum up what we found with continental drift. Wegener's evidence was jigsaw fit of coasts, continuity of ancient mountain belts, continuity of major faults, ancient climates, fossil distributions. This is a heck of a lot of evidence, right? So the scientific community said, yeah, Alfred, I like it. No. Alfred, when he suggested this, was ridiculed in the scientific community. They mocked him, they teased him, they actually kicked him out of societies. They were awful to him. Why? Well, one of the reasons that his ideas were not accepted and mocked is because he couldn't provide a mechanism for continents moving. He knew that they were doing it, but he couldn't say why they were doing it or how. So that's a big problem for scientists. If you're going to tell me North America, this gigantic piece of rock, is moving, that I'm going to need to see why. At this point, the Earth was thought to be completely solid. So how is it possible for a continent to be moving? Now, the second part of this was Alfred Wegener was a German scientist who proposed a lot of his ideas after or during World War I. And during World War I, Germany was considered to be the enemy to many countries, especially the United States and European allies. So, German scientists really weren't looked upon with favor during this time. And this is a lesson that human biases can often get in the way of science. So we actually, as a scientific community, said, nah, we're not going to listen to you. We don't really like you as a person. So there's one reason it wasn't accepted. So a couple of years later, after he proposed his idea and he was made fun of, he died on a geological expedition. He actually froze to death. And he never knew that his ideas would eventually shape one of the most powerful geologic discoveries of the 20th century. So we kind of leave continental drift alone for like 30 years or so, just about. No one accepts it. But there's going to be a finding in the 1950s that really changes that opinion. And what that's going to be is our understanding of paleomagnetism and Earth's magnetic field. So Wegener's hypothesis is eventually going to be supported by geophysics. So what you're looking at here is the magnetic field. We have the North Pole up here, South Pole down here. Okay, makes sense? Excellent. So Earth's magnetic field resembles a simple bar magnet, meaning one side repels, one side attracts. We have a north end and a south end. However, unlike Earth's shape, the shape of our field is not spherical. And what that does is it causes the angle of the magnetic field to change with latitude. All right, so here we have Earth. Latitude is this direction. Okay, so the bands are going this way, all the way up. So here's what this looks like in principle. I don't need you to memorize any of this. I'm just telling you a little bit about how it works. Here we have South Pole. Here we have the North Pole all the way up here. And you see how this magnet actually flips itself down. Well, what this means is many rocks are actually created with magnetic signatures. They have iron in them, and iron is magnetic. So if I find a rock, I can figure out which direction it's pointing. If I have something that's pointing like this, I can find that that should go near the equator. So if rocks have moved through time, I can eventually find out their ages and then find out what their magnetic signature is and start to piece it together. So, okay, how does this weird magnetic rock magic have any relevance to plate tectonics? Well, let's explore this. So, again, rocks preserve magnetization where they form. This is what it looks like. We're not going to worry too much about the Curie temperature, but it just means below a certain temperature, rocks will have magnetics. That was designed after Pierre Curie, not Marie. All right, so this is what this looks like. Rocks are preserved in a certain direction, meaning we can use them to make a giant jigsaw puzzle of what Earth used to look like. So, how we do this is we take rock samples out of cooled lava, usually from volcanoes. This is basalt, so this is like a Hawaiian volcano. And we can figure out what direction the magnetic field was when it was formed. Does the magnetic field now stay unchanging? It absolutely doesn't. We experience magnetic reversals. What that means is, I just told you the bar magnet north points towards the North Pole. That's not actually always true. In a normal polarity, normal means that north magnet is pointing straight up towards the North Pole. And in the southern hemisphere, the southern part of that magnet is pointing towards the South Pole. Makes sense, right? North goes with north, south goes with south. Well, sometimes we have reversals. So take a look here at these teeny tiny little arrows. North is here, south is there. North here, south there. The magnetic flips up and down. Now, we don't know why it does this, not really. We don't know how long it takes. It doesn't do it on a timeline that we understand. If you look at this bar here, you see that it's not happening on a steady timeline, but it does do it. So normal polarity means the north end of the compass points towards geographic north. So north points towards north, that's normal. Reverse is when north points towards south. So let's see how we can use this to figure out plate tectonics. Real quick, the sun actually also does these magnetic reversals. For 11 years, north becomes south, south becomes north on the magnetic pole. So it takes about 22 years for a full magnetic cycle in the sun. So how do we first observe these magnetic reversals? We did this by looking at magnetic strips on the ocean floor in the 1950s. Now, in the 1950s, we had just finished World War II, where we had developed a lot of sonar, a lot of submarine technology because we were looking for weapons in the ocean. And then we immediately move into the period of the Cold War, where we're wildly suspicious of things. And we are trolling the oceans trying to figure out what's going on with our enemies. So, I'm not a human historian, so if anything I've said sounds a little weird, my apologies. So what's going on here is geologists pick up all of this extra cool stuff that we're doing. They're like, ooh, cool, we can do all kinds of research with all this new technology. So along this mid-Atlantic ridge, which is what this is right here, mid-Atlantic ridge, it's labeled, you see that there's blue and gray, normal and reverse. All right, now also notice where the position of this mid-Atlantic ridge is over Iceland. That's important. So, seafloor spreading. We see that at these mid-Atlantic ridges, or at the mid-Atlantic ridge, that the stripes are actually moving away. The plates that we're sitting on are moving away from each other. All right, so here's our ridge, and it's getting wider and wider and wider. More stuff is coming out of it, okay? So this is 9 million years ago, we have just this. 6 million years ago, we have even more. 3 million years ago, we have even more. And this is what's coming out today. Normal, reverse, normal, reverse. We can date those normal and reverse things to figure out how long ago these happened. So now, how was this discovered? Well, let's take a look at two people from history, Marie Tharp and Bruce Hazen. Bruce Hazen was a famous scientist, or pretty well-renowned scientist at the time, and Marie Tharp was his, please note that I am putting this word in quotation marks here, secretary. She went on all of the expeditions, she did a lot of the data collection, but she was his, quote, secretary. She made this map. This is pretty much due to her scientific discoveries here. So here's North America. We've got that mid-Atlantic ridge running right through Iceland, just like we just saw, running all the way down through here. All right. And while they were on this expedition, they were taking images of the sea floor using sonar and things like that. And she started seeing things like volcanoes. She started seeing things like mountains under the sea floor. And she said, you know what, Hazen, I think the oceans are actually spreading. I think the mid-Atlantic, or I think the Atlantic is actually growing. I think that that's why we're seeing these normal reverse polarity things. I think that's why we're seeing what we're seeing. Hazen looked at her and dismissed her ideas as girl talk. He later published her ideas and gained international notoriety, becoming an incredibly famous geologist. She was not an author on the papers of seafloor spreading. After Hazen died, however, she published on her own, and she actually took back credit, and she won a professorship at Columbia University in New York. But what this means here is that scientists and science institutions often follow the culture of the time. That means that women's and other underrepresented groups' achievements are often overshadowed, or even worse, taken from them without their consent. The scientific community is still working to do better every single year, to be more inclusive and to respect the ideas of traditionally underrepresented groups. So Marie Tharp here didn't get the credit she deserved when she was alive for her ideas of seafloor spreading. I give her, but we should honor her now. So Marie's ideas were confirmed by seafloor drilling into the seafloor. So the youngest rocks are near the spreading center. They get older away from those spreading centers. So take a look here. Where is North America? Right here. Excellent. You see this here. This is corresponding to the youngest ages, and those ages are down here. As we get further and further away, they're getting a little bit older. Okay? Now, how can we tell about these ages? Well, we can radiometrically date them. Now, this yellow line that we talked about in the first bit of lecture is a spreading ridge. How very exciting for all of us. All right, so seafloor spreading. How we figured out plate tectonics. We found a mechanism for the plates to move by spreading apart. Excellent. Where's the problem? Well, the problem is that if we're continuously generating new material, then Earth should be growing in size. Is it growing in size? Absolutely not. This violates many laws of pretty much all forms of science. So what do we need here? If we're making new stuff, we're going to have to do what? We're going to have to destroy old stuff. So this is called the process of subduction, the process by which the ocean floor sinks back into Earth's interior. This happens at subduction zones, and this is the source of many of our famous volcanoes and earthquakes, not San Andreas, but other ones. So here we have subduction. All right, so what we see here is one plate going this way, one plate moving this way. One plate is actually being forced down underneath the other and returning back to the mantle. All right. So now that we've got this, we've got subduction, we've got seafloor spreading, we've got the fit of the continents, all this stuff, we've got enough to elevate plate tectonics to a theory. So here it is, plate tectonics, Earth's rigid outer shells broken into pieces that move along Earth's surface. And that is the theory of plate tectonics. Each plate is separated by a boundary. These boundaries are constantly moving. For example, the Cocos plate here is constantly moving under the Nazca and the North American plate, which causes massive earthquakes, most famously recently in Mexico City. We also have many earthquakes that are along this boundary here. The Nazca plate is subducting under the South American plate. The Arabian plate and the African plate are moving further away from each other every second. So rewind real quick. What does the inside of Earth look like? We have our core, we have our mantle, our inner core, outer core, we have our mantle, we have the lithosphere, which is this part right here. We have the asthenosphere, which is this melty, gooey thing. Imagine if you heated up silly putty, that's kind of what the asthenosphere would be. Not totally solid, but also not liquid. And so we're moving based on what the asthenosphere is doing. We're kind of just going along for the ride. So now the crust. There's two types, oceanic, continental. We live on continental crust. Oceanic crust is where the oceans are. Oceanic crust is much denser than continental. And the reason for that is the material that makes up each of these two types of crust. Here we have basalt. Basalt is primarily, it's made out of minerals like olivine. You do not need to know what I'm about to say, but olivine has a mineral formula of magnesium, iron, that's primarily magnesium and iron, so that's why it's so dense. Granite is not nearly as heavy in magnesium and iron, so it's less dense. There are 3 types of plate boundaries involving these types of crust. The first is divergent. So this is going to be a little harder over video, but I want you to take your 2 hands and move them apart for me. So put them together and then move them apart. This is a divergent plate boundary. They're moving away from each other. Okay? So just like Robert Frost said, two paths diverge in a wood, that means they're moving away from each other. A divergent plate boundary starts with the continent being torn apart. So imagine with me you've got a Snickers bar. All right, better yet, pause this video, go get yourself a Snickers, and then do the demonstration and have a delicious snack afterwards. All right, take the Snickers bar in your head. Start to pull it apart very slowly. Okay? When this happens, you're going to see some cracks form, just like you're seeing right up here. You're going to see some cracks form. You're going to continue pulling. And what you're going to see is this crust here is going to get thinner, just like your Snickers bar is going to get thinner where you're pulling. It's going to drip a little bit. You see this here? This is your caramel starting to drip. Continue to pull apart. Eventually, the 2 pieces are going to snap into 2. This is the process of a divergent plate boundary, kind of pulling apart from one another. All right. So where do we see this happening? Does this happen on Earth today? Well, if plate tectonics is true, then it should be. It absolutely does. So right here, we have our Snickers bar, otherwise known as the African Nubian plate, and the Arabian plate right here. They are pulling apart very slowly. This is our Snickers bar in action. Between these 2 plates, water has rushed in, making the Red Sea. We have all of these rift basins forming all along this place. So since the crust is getting thinner where it's pulling, water will start piling up in lots of places. For example, like Lake Victoria, or down here with Lake Tanganyika. All of these are filling in with water because of all the pulling. So there you go. So features associated with divergent plate boundaries, we definitely have volcanoes. That's where a lot of that lava is coming from and seeds are spreading. And we do have earthquakes. Let's use this as a car analogy. Let's say you and your friend own pickup trucks. You tie your pickup trucks together by the ends of them with a rope, and then you try to drive in 2 separate directions. You'll definitely feel a tug when you reach maximum distance apart, but it's not really going to affect you too much. Okay, there'll be a little shake, but not too bad. That's what an earthquake is like at a divergent plate boundary. The second is convergent. All right, now if a convergent plate boundary is, or if a divergent plate boundary is, move your hands with me, moving away from each other. Convergent means together, so move your hands together. All right. So there's 3 types based on the material colliding. There's oceanic, meaning 2 types of oceanic crust hitting each other. Oceanic continental, and continental. All right. So now we know in a convergent plate boundary we should see, or a lot of the times we see, subduction happening. This is pretty important. How do we figure out which plate is subducted? Density. Okay, so which one is more dense, oceanic or continental? Well, you know this, it's oceanic crust. Now, what if we had an oceanic boundary? That's going to be a little more difficult, isn't it? Actually, not really. So ocean crust is more dense, okay? Always. Old oceanic crust is slightly more dense than new oceanic crust, okay? And the reason for that, as things get colder, they generally increase in density, all right? So remember fire safety here. If the room is filled with smoke, cold air will sink because colder air is denser than warmer air. So you should always crawl out of a room that's on fire instead of running, all right, or walking. So colder crust is older. Older crust is more dense, all right? So if you want to remember this, the colder, older will subduct. That works with me. So in an oceanic plate boundary, whichever one is oldest will be the one that subducts. With convergent plate boundaries, we usually see very large earthquakes and a lot of volcanoes. So if you imagine with me in our car scenario, if you hit another car head on, that would be the type of earthquake type you would associate with this. So very bad. All right, the world's worst earthquakes happen at convergent plate boundaries. Now take a look at this graph here. This is the age of the seafloor. It starts with 0 million years ago to 280 million years ago. All right, this is where we have some of the oldest here. It was recently discovered. All right, some of the oldest here, they're rimming the edges of these continents, but pretty much everything stops at about 170 to 180 million years ago. Now, the age of the Earth is 4.56 billion years, so why do we only have a teeny tiny bit of that as ocean crust? Well, remember, older oceanic crust gets more dense, so ocean crust generally always subducts. There are rare instances where some of it is saved, but 99.999% of the time, it's going to subduct. That's why we don't have very old ocean crust. And this is the Wilson cycle. I do not need you to memorize this. I want you to know the very basics, as in this starts when we start pulling apart a continent, and it ends with an ocean being subducted. All right? You should be able to tell me the general stages of where the different oceans are. So if the Atlantic is still growing, it's in a fairly juvenile stage. The Red Sea, of course, is just starting to split, so that's also in a very juvenile stage. The Pacific is converging, meaning it's in an elderly stage, near the end stage, okay? I'll be very simple with my words so you can figure out what I'm asking. So again, here we have our Wilson cycle. Here's the North Atlantic, it's still spreading. Here's the Red Sea. It is still spreading. You see this is the youngest, this is slightly older. The Pacific Ocean is rimmed by convergent plate boundaries, meaning it's getting smaller every year. So it is in the ancient phase. So here's the Pacific. What is this showing here? What do you notice? You should be noticing a lot of these dots and triangles. These are volcanoes and earthquakes. So this is actually tracing plate boundaries. This area on Earth is called the Ring of Fire, just like the Johnny Cash song, but I think he had a very different definition of the Ring of Fire when he made that, song. So what you notice here is that along this boundary, we have a lot of earthquakes, we have a lot of volcanoes. Now, here's Hawaii. Is Hawaii being affected by the convergent plate boundary? No. Right? Hawaii is very far away from even the closest plate boundary there is. So Hawaii's volcanism is actually not related at all to the Ring of Fire. It's related to something totally different called a hotspot, something we'll talk about a little bit later. Okay, so now the third type, just to be clear, we're not going to worry too much about this one, but it does happen, is transform. So do a divergent plate boundary for me real quick. Make a convergent plate boundary with your hands. Now transform. Take both your hands, place them side by side, and move them past each other, okay? So plates are slipping past one another. So this is the famous example, the San Andreas Fault. We do have earthquakes, so if you imagine the car crash scenario again, this would be like sideswiping something. Not nearly as bad as a head-on collision, but still something you'd like to avoid. Now, how fast do these plates actually move? On average, they move about 30 millimeters, which is 3 centimeters per year. So the average annual growth of fingernails. Some are moving a little bit slower, some are moving a little bit faster. It just depends, okay? But the average is about 3 centimeters through 30 millimeters. And here's what that looks like, again. So now, why do we have plate tectonics at all? This is an excellent question. We're not the only planet or body in the solar system that has them. Europa, which is one of Jupiter's larger moons, also has plate tectonics. They work in a very different way, but still has plate tectonics. And plate tectonics have a heck of a lot to do with how life has evolved on Earth. So plates moving cause great shifts in climate. Plates give us volcanoes, which have shaped the landscape of Earth dramatically. We'll talk about all this next couple lectures. So here are your review questions. All right, have fun.